Alright, so in this video we go over section 9.3, the complex plane. So in this section we are going to plot points in the complex plane and then convert complex numbers into different going to rectangular form, polar form, and also exponential form, and then do operations with complex numbers, which is in this case multiplication and division, and in using the polar form and the exponential form. And then we're going to use the De Moivre's theorem to evaluate powers of complex numbers. And then we close this section finding complex roots. Alright, so what are we going to do in this case? Well, so a point x, a complex number has this form z equals to x plus yi, in which the real part corresponds to the x-axis and the imaginary part of the complex number corresponds to the y direction. So ultimately graphing complex number is the equivalent of plotting a point x, y. Alright, I is the imaginary unit to denote that whatever number gets multiplied by I means it goes in the y direction. Alright, so let's see. Let's plot the corresponding point. The corresponding point to z equals the square root of 5, negative 3. In this case, this is x, this is y. Well, y equals negative 3 and x equals the square root of 5. But the square root of 5 is, using a graphing calculator, well, the square root of 5 is 2.23. So basically here and negative 3. Alright. And of course, from the x-axis it has an angle and all that we are going to find. Alright, so in this section we're going to do some connection between the polar coordinates and the rectangular system, and then the rectangular coordinate system, and connect those two systems to plotting complex numbers, because ultimately complex numbers, again, these numbers are going to form a triangle, if you will, in which x would be related to arc cosine theta and y will be related to r sine theta. Well, in this case, the radius is not going to be called the radius of the circle or the hypotenuse of the triangle, because in this case, the point which is located at x comma I y, it's gonna be some distance from the origin to whatever that point is, and that distance, we don't call it distance again as well, we call it magnitude or modulus of z, and it's denoted with as absolute values, and it's simply the square root of x squared plus y squared. Another way to represent this is multiplying z times z bar, where z bar is the complex conjugate of z. For example, okay, let me do this, z times z bar. So z is the number x plus I y, and its conjugate, it's going to be the same but with a negative sign. So I'm going to FOIL this. That's x times x, that's x squared, and then x times negative iy, that's a negative I x y, and iy times x, that's plus I x y, and iy times itself, positive times a negative is negative I y squared. And then in this case, these two quantities go away, and x squared equals to x squared minus I squared times y squared. But what's I squared? If you remember from basic complex numbers, I squared equals to negative 1. So this is x squared plus, or actually minus negative 1 times y squared. That's the same as adding x squared plus y squared. And that's how we verify this equality right here. It's the same. Alright, let's do some examples converting complex numbers between the rectangular form and the polar form? Well, all we do is that we need to make sure that r is a positive number, and the angle, actually the angle is typically called the argument of the complex number. And all we do in this case is replace x and y with their corresponding expressions in the polar plane. That is, x is r cos theta and y is r sine theta. There's no it's really the same. X equals r cos theta and y equals r sine theta. And of course, typically what we do is factor out r. So that is the form to represent a number, a complex number in polar form. Then we're going to use this form to express, actually all we need is the radius and the angle, or the argument, to represent this using the exponential form. But before discussing that, another way to express this, many textbooks use r cis theta to shorten the notation. And in this case, this c means cosine, I sine, and then because they share the same angle, well, we don't need to write the whole thing as r cis theta. All right. However, most likely on the homework, when you input your final answer, it might be in either cosine and sine notation or in exponential notation. How do we do the exponential notation? So we're going to use Euler's formula. It's spelled E-U-L-E-R, Euler, but it's actually pronounced Euler's. It's Euler's formula. And Euler's formula tells us that cosine theta plus I sine theta equals to e to the I theta. It's one of the most important results in mathematics and complex analysis or complex variables, and it's applied widely in many applications, not only in the complex variables area, but actually in solving other equations or higher level equations called differential equations, and amongst many other applications. So doing a proof of this formula, it's a little bit beyond the scope of our course. We would need to know a little bit more of infinite series, which, well, it's something that we haven't covered in this class. So we just take this formula and all we do is replace cosine theta plus I sine theta, replace that with e to the I theta. Alright, so we're given an example. Write an expression for z equals square root of 3 minus I in polar form and in exponential form. So what do we do in this case? Well, first identify that x equals root of 3 and y equals to negative 1. That's the number that multiplies the I, the imaginary unit. Let's find the radius. Well, it's not the radius. It's actually, in this case, the magnitude or the modulus, which is the square root of 3 squared plus the square plus negative 1 squared. And in this case, well, that's a square root of 3 plus 1, and that's the square root of 4, which equals to 2. And then now we need to find the angle, the argument. Well, keep in mind that if you know x and y, the angle or the argument is the inverse tangent of y over x, which in this case the inverse tangent of negative 1 over root of 3. Well, inverse tangent of negative 1 over root of 3. Well, if it works better for you, you might want to write this as tangent negative 1 of negative 1 half root of 3 over 2. That way you can look at a point in the unit circle where y equals to negative 1 half, that is, and then x equals to, you know what, this is square root of 3 over 2. And in this case, the angle in question would be 11 pi over 6. All right. So in this case, what are we going to do? Well, let's write z equals to square root of 3 minus I equals to r which is in this case 2 times cosine of the angle 11 pi over 6 plus I sine 11 pi over 6. That's all we do. Just put that in the formula and then change that to actually exponential form. That's only r, which is 2 e to the I pi over 6. All right. Oh, actually 11 pi over 6. So I like writing the number first as a coefficient, 2 e to the 11 I pi over 6. Final answer. And so this is exponential and this is polar. We need to express both as final answers. Alright, so over here let's plot the point corresponding to z equals to 2 cosine pi over 6 I sine pi over 6 equals, so in this case I need an extra 2. That's the radius as well in the complex plane, and write an expression in rectangular form. So ultimately what we're doing is simply simplifying these numbers. So 2 times cosine of pi over 6 is the square root of 3 over 2 plus I sine of pi over 6, which in this case is 1/2. And that's it. That's all we have to do. 2 root of 3 over 2, that's simply root of 3, plus 2I over 2, that's simply I. And then we need to plot this. Well, I mean, it's really not that nothing crazy. Square root of 3 and 1, right? That's the point. That's the point. Z equals to 2 e to the I pi over 6, or the point root of 3 or root of 3 plus I. All right. So what we do again, simplify, evaluate the trigonometric functions, and simplify and plot the point. There's really nothing crazy about it. Okay, so let's do operations like products and quotients of complex numbers. Well, so in this case, well, if you read the book, you're not going to see this, well, this is not Euler's formula, it's something else. This is just some definition. You will see this as a cosine I theta 1 and cosine plus I sine theta 1. In other words, you will see these two in terms of sines and cosines. However, I'm using the exponential form because that notation is way shorter to avoid writing too many sines and cosines. So what's that we have to do? Well, so we are going to multiply ZW. Okay, but first of all, let's express Z using exponential form, and in this case that's the radius R1, which is 4, e to the 2 pi I over 7, and W, that's going to be 9 e to the 5 pi I over 7. Okay, so what we do here in this case, well, is simply multiply these two, and again, instead of writing this whole thing, this number times that number, well, that's a lot of writing. Change to exponential, do it quicker. 4 e to the 2 pi I over 7 times 9 e to the 5 pi I over 7. And all we do is simply use laws of exponents. That's all we have to do. You know, so 4 times 9, multiply the coefficients, that's 36. e to the same base is the same is e. All we do is add the coefficients. 2 pi I over 7 plus 5 pi I over 7. And the final answer to this will be 36 e to the 2 7s plus 5 7. That's 7 7/7. But this reduces to e to the simply pi I. Now, well, this is the exponential representation. We need to also represent it in polar form. 36 cosine pi plus I sine pi. All right. And then in this case, we can evaluate cosine of pi -1 and sine pi, which is 0. That'll be 36, our final answer. But we can leave it like this. Let's perform the division this time. Let's divide. Okay, leave the two numbers here. And so this is going to be 4 e to the 2 pi I over 7 over 9 e to the 5 pi I over 7. Alright, 4 divided by 9 is 4/9. And well, in this case, we're going to use laws of exponents. When we divide the same base, what we do is subtract the exponents. 2 pi I over 7 minus 5 pi I over 7. In this case, be careful with the result for the division in the case that you get a negative angle, because we are going to get a negative angle. So in this case, 4/9 e to the 2 minus 5 is in that negative 3 pi I over 7. Of course it is. That's what it is. However, in this case, we have a problem here. What's the problem with this? Well, the problem here is for the complex numbers, the argument theta has to be between 0 and 2 pi. That is, no negative angles and no angles larger than 2 pi or 360 degrees. So in this case, we have a problem with that. We have a problem over here with this being 3 pi over 7. So let me just do a plot. Negative 3 pi over 7 is right here. So we need, in this case, to add 2 pi to fix the issue and turn it into a positive angle that lies between 0 and 2 pi. And in this case, 7/7, 2 times 7, that's 14 minus 3. 14 minus 3, isn't that 11? So this is going to be 4/9 e to the 11 pi I over 7. And that's final answer in exponential form. We're using the polar form, 4/9 cosine 11 pi over 7 plus I sine of 11 pi over 7. So the two answers together. Polar exponential using Euler's formula. Alright, de Moivre's theorem. So it's written de Moivre's, but it's actually pronounced de Moivre. The Moivre, that's how we pronounce this this last name. It's a French, after the French mathematician whose last name is de Moivre. I believe it's Joseph's his first name. Can't forget a moment. So in this case, well, we have a complex number z. Doesn't matter if it's 1 or 2. Doesn't matter, just a number. And we use this theorem to evaluate powers of complex numbers. So this is going to be very powerful for that. I'll show you why. So ultimately, what we do from z equals r e to the I theta, all we do raise both sides to the n power, not to the second power, and we're gonna get z to the n, I theta times n, e to the I n theta, and r to the n, that's r to the n, which is this formula right here. All right, so we use that to raise complex numbers to the nth power. All right, for example, in what if you want to raise 1 plus I to the second power? Well, this one is really not that bad to do, so you don't need to write this. If you don't want, that's fine. So, well, that's 1 squared, which is 1 plus 2 times 1 times I plus I squared. So in this case, 1 plus 2I minus 1, which is I squared, and then 1 minus 1, that's simply 2I. But what if you want to raise 1 plus I to the fifth power? You know, do you want to FOIL this 5 times? No, you don't want to do that. You don't want to FOIL that 5 times. That's the power of the Moivre's theorem, to raise powers of complex numbers. So let's do one example. Let's do one example over here. So express the quantity 2 cosine pi over 9 plus I sine pi over 9, the whole thing cubed. Well, in this case, we are given a really nice complex number already in polar form. Let's first of all raise it to they want us to actually cube it. They're actually asking us to cube it. So how are we going to cube this number? Well, essentially, the quantity that lies inside of the curly braces here, let's write it in the REI theta form. That is 2 times e to the I theta. That's pi. Did I say in this case I pi or a pi I? Okay, pi I over 9. The whole thing to the third power. And what do we want here is raise this to the third power, raise this to the third power. But in the first case, 2 to the third power, that's 2 to the, well, let me write it 2 to the third power, and then e to the pi I over 9. Power over to another power, we multiply the powers. So that's 2 to the third, that's 8. E to the, well, 3 pi I over 9, 3 over 9, that reduces to pi I over 3. So that's the answer in exponential form. They're asking us in this case to raise this to actually write it in rectangular form. In order to do that, we need to go back to polar first. And well, cosine pi over 3 in this case is 1/2 plus I sine pi over 3. Sine pi over 3 is the square root of 3 over 2 times the imaginary unit. All right, and then, well, let's distribute the 8. 8 times 1/2, that's a 4. And 8 times square root of 3 over 2, that's also 4 root of 3. I. All right. So actually, when I write complex numbers that involve radicals, I like writing the letter I in front of the radical, and the reason for that is because sometimes when writing this, we go a little bit over the radical symbol, and we do this and we think that the I lies inside of the radical, which is not the case. I is outside of the radical. So my advice, you don't have to do that if you don't want, if you feel okay doing this, but I preferably write I's in front of radical symbols. express I to the 1 plus I to the 5th power, which is what I said earlier. Do you want to FOIL that 5 times? I mean, it's doable, but you don't want to do that. We're going to use the power of polar and exponential form. So in this case, let's write this in polar, and then so let's consider actually z equals to I plus I. Well, I mean 1 plus I. So that's the number inside. That's some complex number z. So the modulus, which is absolute value bars of z, that's the square root of 1 squared plus 1 squared, which in this case is the square root of 2. Alright, let's find the angle, which is tangent inverse of 1 over 1, which is tangent inverse of 1, which equals to pi over 4. Well, I mean, plot a point, 1 comma 1, that's 45 degrees, or pi over 4. And you might want to, let's first write this using r cosine theta. All right, let's go ahead and do that. And well, from here what I'm going to do is square root of 2 e to the I pi over 4. All right, so what I'm doing is writing this in exponential form, which is more convenient. Now we want the 5th power of this. So the 5th power, I'm going to go z to the 5th power square root of 2 e to the I pi over 4 to the 5th power. Well, c to the 5th power equals, okay, number 1, the 5th power would affect the square root of 2 and would affect the exponent of the exponential factor. Now, what about square root of 2 to the 5th power? Let me do it on the side. Let me reduce that on the side. Square root of 2 to the 5th power. This is the same as 2 to the 5th because of when you have the nth root of a to the m, it's the same as the nth root of a, the whole thing to the m. So I'm basically inputting this inside, and then 2 to the 5th is the square root of 32. Then I'm going to reduce the square root of 32 as the square root of 16 times 2, and 16 is the square root of 16 is 4. The square root of 2 is simply 2. So I'm gonna go like 4 square root of 2 times e to the I, actually 5i pi over 4. All right, and that's how we raise a in this case, well, 1 plus I to the 5th power. That's going to be 4 square root of 2. Let's write this in terms of cosines and sines. For square root of 2 cosine pi over 4. Oh, I mean cosine 5 pi over 4. 5 pi over 4 is in the 3rd quadrant. Both cosine and sine are negative values. In this case, negative root of 2 over 2 plus I root, actually minus root of 2 over 2. And well, let's see, how do we reduce this? Distribute. 4 divided by 2, that's going to be 2 times the square root of 2 times itself, which is going to be 2. And the same, well, actually negative, and then minus I times 2 times 2, which is actually negative 4 minus 4i as a final answer. All right, if you have time and you're you have some free time, you want to do this foiling this 5 times, you should get -4 minus 4i. But in the meantime, we are using the Moab's theorem in order to actually erase powers of complex numbers in a way shorter way. All right. The last part of this section is to find complex roots. So, what's the motivation for finding complex roots? Well, so you might remember when you solve the equation x squared plus 1, x squared plus 1 equals to 0. That's x squared. Well, that's not a good paper. Let me get another one. Okay, so x squared plus 1 equals to 0, x equals plus or minus I. You know, it has two complex solutions actually. 0 minus I, 0 plus I. So those are two complex solutions. Now, what if you want to solve the equation, the cube root of x cubed plus 1 equals to 0? Well, the most typical way was to go x cubed equals to -1 and x equals the cube root of -1, which is -1. But in this case, we're obtaining only one solution. The degree of the equation is degree 3. However, in this case, we have only one solution. What about the other solution? So this is why I would go about the with a different way. X cubed plus 1 equals to 0. Instead of using the cube root property in this case, or the root property, general root property, I would factor this as a sum of cubes. X plus 1, x squared minus x plus 1 equals to 0. On the one hand, yes, x equals to -1. But over here, well, factors of 1 that add up to -1, well, that's not possible. In fact, we would have to use the quadratic formula. So minus b plus minus the square root of b squared minus 4ac. The whole thing divided by 2 times a. Well, in this case, that's 1 plus or minus the square root of 1 minus 4 over 2. And you might remember this from intermediate algebra. Well, when you got solutions like this, you express them as complex numbers. So that's 1 plus or minus I root of 3 over 2. So that's an x1, which is -1. The other solution would be x2 equals to 1/2 minus I root of 3 over 2, and x3 equals to equals in this case root of 3 over 1/2 plus I root of 3 over 2. Right, let me actually Alright, so 3 solutions. And the same happened for, I don't know, x to the 5th power equals to, x to the 5th power plus 32, for example, equals to 0. X to the 5th equals -32. X equals the 5th root of -32, which equals -2. But that's only one solution. What about the other 4 complex solutions? So that's what this formula is for, to find the remaining solutions of a complex equation. You know, so let's do an example. So the formula is right here. So zk, where in this case k would be every iteration of the solution that we are going to find. So for example, if we want to solve an equation of 5th degree n equals 5, k would be n minus 1, in this case 4. We're going to go from 0 all the way to 4. We're going to do the calculation 4 times. Well, let's do an example. I mean, just looking at the formula, yes, looks pretty, but it's better if we see that formula in action. So let's go ahead and look at one example. Find the complex fifth roots of -1 plus root of I. In other words, they're asking us to solve x to the fifth power equals to -1 plus the square root of 3i. So they're asking us to solve x equals to the fifth root of -1 plus 3i. Kind of crazy, looks kind of crazy, but yes, it's not a unique solution. There's going to be actually 5 solutions. So number 1, how are we going to go about this one? Well, number 1, let me express the point z equals -1 plus I root of 3, and let's find actually we don't need to have this this point in polar and then exponential there. All we need to know is to find the magnitude or the modulus of the complex number, which in this case is the square root of -1 squared plus square root of 3 squared. So that's 1 plus 3, which equals 4, and the square root of 4 is 2. So the modulus is 2. Alright, let's find the angle. So in this case, the angle theta equals tangent inverse of, in this case, y, which is root of 3 over -1. Well, in this case, again, this one is a little bit tricky to see. So tangent inverse root of 3 over 2 over -1/2. So we're looking for the angle theta for which y equals square root of 3 and x equals -1/2, and this one happens to be 2 pi over 3 actually. All right. So let me just verify that real quick. Give me 1 second. So mode degree inverse tangent of negative square root of 3. Okay, yeah, so that's a -60 plus 180. Yep, that's 120 degrees. Yep, that's 2 pi over 3. All right, so what are we going to do? Okay, first of all, let's write the Moivre's theorem formula. Let me copy it. So in this case, zk equals to the nth root of r e to the I 1 over n theta plus 2 k pi, multiples of pi. In this case, k would depend with the iterations based on n. In this case, well, we're looking for the fifth root. That means in this case, n equals to 5 and k equals to, it's going to go from 0, 1, ... 4. Okay. So what are we going to do in this case? Well, so in this case, for k equals to 0, well, number 1, let's write down zk. Zk is n, which is 5, the fifth root of r, which in this case is 2, e to the I times 1 divided by n, which is equals to 5 times theta plus 2k pi. In this case, we're gonna go k from 0 to 4, that is 5 times, to find the fifth root, the 5 fifth roots of -1 plus square root of 3i. Okay, so let's do first of all for k equals to 0. So that's z subscript 0. That's the square root of 5, the fifth root of 2, e to the I 1/5 times the angle. Actually, I should have written the angle instead of just theta. That's 2 pi over 3. So that's 2 pi over 3 plus 2 times 0 times pi, because k is 0. Alright. So in this case, well, what are we going to have? Well, so 2 times 0, which is 0, 2/3 times 1/5, that's going to be 2 over 15. So the fifth root of 2 e to the 2 pi I over 15. That's the first solution. All right. For k equals to 1, that is z subscript 1, that's the fifth root of 2, e to the I times 1 over 5, 1/5, times 2 pi over 3, plus 2, instead of 0 this time it's going to be a 1, times pi. Alright, let's simplify this. 2 times 1 is 2. 2 pi plus 2 pi over 3, well, that's 2 times 3, which is 6. 6 times 2, 6 plus 2, that's 8. So the fifth root of 2, e to the 2, that's 8, pi I over 15. Alright, so that's the second solution. K equals to 2, z subscript 2, the fifth root of 2, e to the I 1 over 5, 2 pi over 3, plus 2 times 2 pi. So that's going to be 4 pi. 4 times 3, that's 12. 12 plus 2, that's 14. And in this case, 14 pi over 3 times a fifth, that's a 14 pi I over 15. Alright? So k equals to 3. K equals to 3. So this is the fifth root of 2 again, e to the I 1/5 times 2 pi over 3 plus 2 times 3 times pi. Okay, so in this case, what do we have? 2 times 3, that's 6. 6 times 3 is 18. 18 plus 2, that's a 20 pi over 3. But 20 pi over 3 times 1/5, this is going to be 20 pi over 15. Pi over 15. But this one, 20 pi, 20 I pi. Let me put the I in the middle here. There's supposed to be an I. This one reduces nicely to e to the 4 pi over 3. 4 pi I over 3. Because 20 and 15 have a common factor. This problem is already taking a good minute. It's very formulaic. We do the last one for k equals to 4. Z equals to c subscript 4 equals to 5 root of 2. The fifth root of 2. E to the I 1 over 5, 1/5, 2 pi over 3, plus 2 times 4 pi, which equals the fifth root of 2, e to the, 2 times 4, that's 8. 8 times 3, that's 24. 24 plus 2, that's 24 plus 2, that's 26. 26 pi over 3 times 1/5, that's 26 pi I over 15. All right? And that's the last answer. Now, suppose for some reason you get confused and by fifth root you for some reason go all the way to k equals 6. Okay, let me just do it real quick and see what happens. K equals 5. So c subscript 5, that's the fifth root up to e to the I times 1/5, 2 pi over 3 plus 2 times 5 pi. So in this case, the fifth root up to e to the, let's see, 2 times 5, that's 10. 10 times 3, that's 30. 30 plus 2, that's 32. 32 pi I over 15. But wait a minute. 32 pi over 15, isn't it the same as 2 pi over 15? Well, how do we know? Well, 32 over 15. 32 pi over, well, I'm going to exclude the pi, 32 over 15. And then I'm going to subtract 2 pi. Actually, let me clear the pi. 32, and then that's going to be exactly the, oh, you weren't able to see this. So what I was doing is 32 over 15 minus 2. We get 2 over 15, which is the same as the k0, 2 over 15. So in this case, k, that's why k only goes from 0 to n minus 1. This one we don't need to do. Of course, from here, what you might want to do is to write this in polar form. Most likely the homework is going to ask you to write both. The fifth root of 2 times cosine 2 pi over 15 plus I sine 2 pi over 15. Same here. Fifth root of 2 cosine 2 pi over 15 plus I sine 2 pi over 15. And so on and so forth. Let me do all of them. I know this example, this exercise, it's already long, but it's a lot of fun. Cosine 2 pi over, oh no, it's not 2 pi, it's 8 pi over 15, 8 pi over 15 over here. (14 pi over 15 plus I sine 14 pi over 15, fifth root of 2, cosine in this case 4 pi I over 4 pi over 3 only, we don't include the I inside, plus I sine, and last but not least, just to wrap this up, 5 root of 2 cosine 4 pi over, not 4 pi, again I was looking at the previous angle, that's 26 pi over 15 plus I sine 26 pi over 15. Final answer, both exponential, polar, etc. And this is the end of this section. This is a good place to quit. I'll see you in the next video.